The objective of Project 2 is to simulate the fused deposition modeling of two different turbine geometries. Multiple thermoplastic materials are to be tested, and we are tasked with determining the best design in terms of geometry and material composition. Additionally, we look into the FDM printing of a single turbine blade and determine the optimal printing orientation, or raster angle, for this FDM process. Our assumptions going into this include no need for support structures, defect-free prints, and no adhesive required on the print bed. Here are the two different turbine geometries we tested, with Design 2 being a bit more complex, with alternating full-length and half-length blades. Design 1 is composed of 10 layers, while Design 2 is composed of 24 thinner layers, and this will be notable later on. The three thermoplastics we tested for the turbine composition are ABS, PET, and polyethylene, whose material properties are given in this table below. And the print bed itself is made of soda lime glass. Additionally, we tested alternating layers of ABS and PET for each design, and this actually gave some pretty interesting results that we'll see in a moment. The meshing strategies of Design 1 and 2 are somewhat different. They both use a tetrahedral mesh, but Design 1 has mesh refinements done at every single layer. Because Design 2 has more than twice as many layers, that same layer refinement could not be done due to the nodal limitations of the student version of ANSYS. However, we did increase the overall mesh resolution and ensured we had at least two elements across any thickness. For boundary conditions, the bottom of the print bed is fixed, and the stagnant air horizontal cylinder convection coefficient is assigned to the print bed. And these are the same for both Design 1 and 2. Our thermal loading is a heat flow of 1e to the negative 7 watts applied at every layer, and again, this loading method is the same for both Design 1 and 2. The FDM process was simulated using element birth and death relationships, and this animation shows the layer-by-layer addition of material. Our temperature results were a little surprising, with Design 2 having the lower maximum temperature in all four cases that we tested. However, for both designs, the deposition of each layer took 10 seconds, so having more than double the layers also meant that Design 2 had double the time to be cooled by that previous convection coefficient. So for equivalent stress, as we just saw, Design 2 had the lower temperature for every material tested, so it makes sense that it would also have a lower residual thermal stress. The most interesting contours are the stress and strain plots for the layered ABS and PET turbines, with Design 1 on the left-hand side and Design 2 on the right. Design 2 has a slightly lower equivalent stress, but its elastic strain is 48% higher than Design 1. This is because ABS and PET did not experience the same amount of thermal expansion during the birth and death process. This is an exaggerated view of the normal stress in Design 2. Every PET layer is under compression, while every ABS layer is under tension, and this is the result of their differences in thermal expansion. This effect is more pronounced in Design 2 because it has more than twice as many layers, so there are more than twice as many transitions from this tension to compression. The remaining results are tabulated in these two tables, and we included the maximum equivalent stress, tensile and compressive stresses, elastic strain, deformation, and temperature. In determining the best design and material, we chose to compare the safety factors of each combination. When comparing the same materials, Design 2 had the highest safety factor in every case. Of the Design 2 options, PET had the highest safety factor at 3.22, so Design 2 made of PET is our recommendation for the rapid prototyping application. We also experimented with the printing orientation on a single blade from Design 1. We were first given a 3D surface, which we extruded to a thickness of 1 millimeter. Using the ACP pre set up in ANSYS, we sliced the blade into 4 layers or plies of uniform 1/4 millimeter thickness. Using the symmetry option in the stack up resulted in our ply angles going 0, 90, 90, 0, rather than alternating, but this was easily fixed by manually assigning the desired angle to each ply. The blade is meshed with tetrahedral elements, and the geometry is not nearly as complex as the full turbines were, so we don't need tens of thousands of elements to ensure accuracy in our results. The flat rectangular surface of the blade is held fixed, and the same stagnant air coefficient that was used for the turbines is assigned to the entire blade surface. The blade is divided up into 4 sections and assigned element birth-death relationships to simulate the FDM process, and each section is assigned a heat flow of 1e to the negative 2 watts. And here is a short animation showing the bottom-up printing of the blade. So first, we look at the stresses present in the blade as a whole. There is a maximum equivalent stress of about 54 megapascals, with maximum compressive and tensile stresses of 11 and 39 megapascals. Now we'll look at the stresses present in each individual layer. We can see about a 3 megapascal increase in equivalent stress of the outer plies, plies 1 and 4, versus the inner plies, plies 2 and 3. Because we need to compare apples to apples, the inner and outer plies are not directly comparable. Comparing the print orientations here, there does not seem to be a notable effect on the equivalent stress. However, when we look at the normal stresses, the 0 degree and 90 degree raster angles result in a significant difference in the normal stresses. The inner layers, ply 2 and 3, the 0 degree angle in ply 3 shows a slightly higher compressive stress, about 3 megapascals higher, but a drastically lower tensile stress of about 26 megapascals lower. And this same pattern is seen for the outer plies, plies 1 and 4. Ply 1, the 0 degree ply, has again about a 3 megapascal higher compressive stress, while ply 4, the 90 degree raster angle, has about a 23 megapascal higher tensile stress. While the equivalent stresses were unchanged, the 90 degree plies have about a 50% more tensile stress than their 0 degree counterparts, so the 0 degree raster angle is preferable. This led to us wondering why the 0 degree direction was more favorable. We figured there were 2 explanations for this. Maybe the 90 degree print orientation resulted in higher stresses because it was perpendicular to our fixed support, whereas the 0 degree angle was parallel to the support. Or maybe printing across the width is preferable due to the geometry alone, unrelated to the relative orientation of the fixed support. We decided to simulate the blade being printed on its side, where each ply would be used as an element in the birth-death process. The fixed support was now applied to the face of ply 1. These are the only differences from our previously shown blade simulation. The 0 degree and 90 degree ply directions have not been modified in any way. They are just shown here to illustrate that they are now both parallel to our fixed support. Here's a short animation showing the modified printing process. The bottom ply being held fixed naturally led to stress concentrations that would not be present in the uppermost ply, so in this case, only the inner plies were compared to each other. This time, the equivalent stresses are significantly affected by print orientation, the 0 degree ply having a max stress 27 megapascals lower than the 90 degree ply. Again, the difference in normal stresses between the 90 and 0 degree raster angles is clear. The 0 degree ply has significantly lower compressive and tensile stresses. With the boundary condition now ruled out as the driving force, we can conclude that the 0 degree print orientation is preferable based on the geometry of the blade. We believe this is due to the uniform length of the 0 degree raster lines. Their length varies less than those in the 90 degree direction. The 0 degree lines continuously and gradually decrease as they reach the tip of the blade, going bottom to top. Whereas the 90 degree lines, going left to right, start short, grow very large, and then become short again. These changes in length occur much more rapidly than with the 0-degree raster angle. To sum it all up, we found that Design 2 made of PET had the best performance due to it having the highest factor of safety out of all the combinations of designs and materials tested. Furthermore, we found that the best printing orientation was the 0-degree raster angle for the shape of our blade. Thank you for listening, and we'll now open the floor for questions.